Let's take a look at how we solve problems like this. Now, we have this inclined plane and then we have a pulley system. Of course, this string is massless and it does not extend. And then we have a mass 3 kg and we have a mass 8 kg. The inclined angle is 30 degrees. So the question says that we should find the acceleration and tension in this system. When you want to solve a problem like this, the next thing that should come to your mind is what we call free body diagram. You must be able to draw a free body diagram of what is really going on in this place. And then it's pretty not that difficult as you might think it. So I'm going to copy this image right here, and I'm just going to paste it down here so that I can draw my free body diagram. So what is a free body diagram? I don't need this. This is just an information that I will come and use later. So let me just delete it for now. Yeah, I don't need this information at the moment. So let me just delete that. Now, to draw a free body diagram, like just like the name implies, free body diagram, you are trying to like analyze the hidden things that are going on in this place. For example, the reason why you were given the coefficient of kinetic friction, which is 0.2, is basically because this particular system, this particular inclined plane, it is not a smooth surface, and which implies that there's going to be another force, which is a frictional force, opposing the motion that is going on in this system. So you do not see that directly in this diagram. But in your free body diagram, that frictional force will have to surface. When you look at this 3 kg, this 3 kilogram, and this 8 kilogram body, they have their weight acting downward. But you can't see the weight right here. But in your free body diagram, you're going to be able to see that. Another thing again is that when something is resting on a surface, when there's an interaction between two surfaces, there is always a counteraction. So as the weight of these 3 kg is resting on the surface, there's going to be a normal reaction. And you can't see that here, but you see that in your free body diagram. Now, in a rope, whenever there is a force at one end of a rope that is attached to another end, rope, string, or any materials of such, there's always tension generated. So I've given you like some details. And so when you want to draw a free body diagram, if you listen to you can rewind it and then listen to everything I've said now. When you have those things at the back of your mind, then you have an idea of what will be in your free body diagram. So let me start with the simple ones. So one thing you should know is that this 8 kilogram, the weight part will be acting downward. So let's draw the weight. So the weight, let me call this one M2 and let me call this one M1. So we have weight 2, which is M2G. And based on what we were given, G is given as 10. So 8 times 10, so that is 80 newtons. You see, as this weight is acting downward, since this is a string, there will be a tension that is acting upward. It is just how it works. It counteracts each other. So tension is always generated in a string whenever there's an applied force at the other end of that string. So the tension will be acting towards the fixed point. So when you have a string, the tension is always towards a fixed point. So let me repeat that again. How do you know tension? When number one, you have a rope, a string-like material. Then you fix this rope at one point. Then you are applying force at the other end. When you're applying the force at the other end, tension will always oppose and act towards the fixed point. And that is how you can determine where tension acts towards anytime. Now, in this place, the tension is always acting along the rope. But the first thing we have to look at here is that the weight of this guy is also acting downward. Yeah, the weight is acting downward, which is weight 1, that will be M1G. And if you do that very well, that will be 30 newtons. So now somebody will say, oh, the weight is acting downward, so where will the tension act? The tension will still act towards the rope because there is a part of this weight that is actually acting on this particular line, but I'm not talking about that yet. So there will be a tension acting in this place as well. Now, because this system is connected, like the system of the first uh, mass and the second mass, they are both connected by the same string, So we can as well say that the same tension that we have in this string is the same tension that we have in this string. And how does that happen? It's simply that if I pull this 8 kg down now, let's say this, I don't even need to pull it myself. The weight is pulling it down. So you can tell that it is the action that this 8 kg is causing that will in turn go and push this 3 kg upward. So you can as well just say that this tension is the same thing that is present in this particular string as well. Now, we are not done. There are other forces that are, if you listen to what I said earlier, there is normal reaction. When you have a surface, when you have a body resting on a surface like this, there will always be normal reaction. And why is it normal reaction? It is normal reaction because it is a reaction that is perpendicular to the surface that you're acting on. So the normal reaction will go up in this manner. So we have our normal reaction. But we are also not done because this surface is not a smooth surface. There has to be a frictional force. So a frictional force. And why am I taking my frictional force in this direction? Please note, frictional force could actually go up, it could go down. The reason why I'm taking this direction for my frictional force is because, as you can see this 8 kg, I'm assuming that the motion is being done by the 8 kg. 8 kg is pulling down on this system. So that means that 3 kg will move upward. So if 3 kg is moving up the incline, frictional force always acts in opposite direction to the direction of motion. So hence, my frictional force has to go down. But if my assumption was that this 3 kg is the one sliding down, I'm pulling the 8 kg up, then it would have been that my frictional force will act in this direction. Now, somebody may ask that, oh, how do I know which one that is pulling down, which one that is not pulling down? Well, you don't really need to know. You can loosely just do this thing anyhow. As long as you obey every principle and then you apply everything correctly, you're going to get the same answer. Just that if you go in the wrong direction, if you solve for your acceleration, you might get a negative result. That would tell you that the direction that you have decided to use is not the right direction. So that is just a pointer. So let's go now. We have everything we need in our free body diagram, nothing else. So I'm going to draw just a broken line to complete this path. So this right hand side, it's quite easy. So let me bring that right hand side out. This right hand side where we have the 8 kg and we have, tension. Then we have, so don't forget, acceleration is downward here. Acceleration is upward here. So we have this tension, we have the weights, 80 newtons. So when you do this very well, this will be tension. Nope, since I always like to use positive for the direction of motion, I always like to use positive for the direction of motion. But in the general way, up is positive, down is negative. So, but in this place, I'm going to be using direction of motion as positive. So that means that anything that is against the direction of motion, they are going to be negative. So let's look at that. So we have direction of motion is downward. So I'm going to take M2G, which is 80 Newton, as the positive guy. So this will be 80. Now, T is the opposite direction, so minus tension. Now, in this system on the right for the 8 kg, there is no other force acting on this system. So only 80 and then tension. So therefore, this 80 minus T would then be equal to, now this is Newton's second law of motion. Net force equals mass times acceleration. What is the mass? Mass is 8. And what is the acceleration? Acceleration is A. So you can call this one your equation 1. So I'm done with that part. Now the part where, there is a little bit of complex stuff to do is this other part. So I'm going to bring that part out. So let me just copy it out. Yeah. Let me copy that out and paste it here. Okay. So you see, when you want to deal with this part, what you need to do first is that we want to rotate this guy. We want to assume that this inclined place, we want to make it our horizontal. And this normal line, we want to make it our vertical. So I'm going to do that now. So I'm going to have this Yeah. So this is my normal and this is my horizontal. So when you look at this now, there are some forces that are acting directly on the horizontal. So as you can see this tension, when you look at it from this perspective, see that tension is going up here. So that is kind of to the right of the horizontal. So you can say you have your force, you have your tension here. Then the next thing you have is your frictional force, which is acting directly to the left. So you have been able to sort the normal, you have been able to sort the tension, and you have been able to sort the frictional force. Now let's go forward. This weight now, where is it acting? First of all, in an inclined plane, I don't want to go through the whole geometry. If the angle of inclination is 30 degrees here, then here as well, it will also be 30 degrees. So I don't want to go through the geometry, so I'm not dealing with that for now. So when you look at where this 30 newtons is acting, you see that this is our vertical, this is our horizontal. It's acting directly in between what? The left hand side of the horizontal and the down part of the vertical. So left and what? Down. So that means that this weight is going to be acting in this place, which is 30 newtons. Now, the angle, of course, is made with the vertical. So you have what? 30 degrees. Now, with this, you are equally done with whatever it is that you are doing. So, but when you have problems like this, one of the things that you need to do is that you need to actually do a little bit of analysis such that you get what we call vertical component and you get horizontal component. So for your vertical, let's look at the forces that are acting in the vertical direction. We have four forces here in total: the normal force, the frictional force, the force of tension, and the weight of the body that is acting downward. So among these four forces, which of them has vertical component, or which of them have vertical component? Whichever one. See, don't mind me on that. Now, normal force, of course, is vertical. 30 Newton is vertical, but if you look at frictional force and tension, force of tension, both of them are directly horizontal. 30 Newton, this 30 Newton has a vertical component and it also has horizontal component. So that implies that I'm going to be taking two of them into consideration. Now, another thing again here is that if you look at the vertical component, there's no motion because this 3 kg is not, neither is it not, it's not jumping up, neither is it what? Being pressed down. So I can choose anyone as my positive. Since at the end of the day, there is no motion, the acceleration along the vertical will be zero. So that will be, so I can say normal force minus, so I need to resolve this 30 newtons to the vertical. Now, based on the fact that this angle is made with the vertical, whenever you want to resolve something and the angle is made with that particular part you are resolving towards, you will use cosine of that angle. So I want to get the vertical component of this 30 newtons, and the angle is made with the what? Vertical. So I'm going to be using what? Cosine of 30 degrees. So that will be 30 newton cosine of 30 degrees. I'm done with vertical stuff. So it's still going to be equals to MA. But because there is no acceleration along the vertical component of this guy, so acceleration is zero. So this is going to be equal to zero. In fact, we can easily get our n like that. Our n is 30 cosine 30 degrees. And that will be 30 cosine 30 degrees. That should be root 3 over 2. And that will be 15 root 3. So you can set that out. So this is in newtons. Now let's go now and do our horizontal component. For the horizontal component, so direction of motion is definitely towards the tension side. So tension will take the positive and anything opposing that will take the negative sign. So we have how many forces in the horizontal component? I think you can answer that. 1, 2, 3, because this 30 has both horizontal and vertical components. So you have force of tension, which takes the positive sign, minus frictional force, then minus 30. Now this time around, now you can see that this 30 newton, the angle, you want to find the horizontal component, but the angle is made with the vertical. So when that happens, what you're going to use is sine of this angle. So you have sine 30 degrees. So, and that will be equal to mass. What mass? This mass, 3 kg, times the acceleration that we do not know. So let's look at this now. Don't forget, generally we know that frictional force, this is something everybody should know. We know that frictional force is mu times normal reaction. Frictional force is mu times normal reaction. So the coefficient, so that means that our frictional force in this place is going to be 0. What was that again? 0.2. Yeah, that is 0.2, that as we have been given, 0.2 multiplied by 15 root 3. So let's sort that out. So 15 root 3 times 0.2. Yeah, I'm pressing my calculator. So that's actually like going to give us 3 root 3. 3 root 3. So from here now we have tension minus 3 root 3 minus 30 sine 30 degrees, that will be 15. 15 equals 3a. So what you need to do now is that we can solve for t in this place. T will then be 3a plus 3 root 3 plus 15. I've just like taken everything to the right hand side. So to you can call this one, let's say, your equation 2. Now don't forget our equation 1. Our equation 1 says that, so let me copy our equation 1 and paste it. So equation 1, we have this. So we can easily substitute what our t is. So our t is 3a plus 3 root 3 plus 15. So we have at minus 3a plus 3 root 3 plus 15 equals 8a. So when we do this very well, we have at minus 3a minus 3 root 3 then minus 15 equals 8a. So you can take the one with acceleration to the right hand side. So we are left with, so 80 minus 15, 80 minus 15, that's 65. So we have 65, don't mind my handwriting. So we have 65 minus 3 root 3 equals 8a plus 3a. So, and that would imply that a, since this one 8 plus 3 will be 11, so that would be 65 minus 3 root 3 divided by 11, and that would be 65 minus 3 root 3 divided by 11. So that's around approximately 5.4 meters per second squared. And to solve for your tension now, so just substitute it into this equation. Since you know your acceleration already, so you just have that at minus tension equals 8a. Yeah, from that equation 1. So that implies that at minus 8a will be equals to tension. Hence, tension is 80 minus 8 times 5.4. And when you do that very well, 80 minus 8 times 5.4, so that's approximately or exactly 36.8 newtons. So you can see we have our acceleration for the system and we have our tension for the system. So to solve problems like this, it's quite easily done. So if you have any further problem or you don't understand some certain things that I've mentioned here, you can let me know. Maybe I'll make a video specifically on that. I'll see you in the next one.